Darkwing duck. Yep. Mighty Ducks. I think that might even be dated. Alrighty. Yeah. Okay, so the first thing we're going to get into is we're going to get into solving equations, because everything that everything that we're going to do is going to be equation based. When I say what is the equation, I'm trying to get you guys thinking, how is all this stuff connected together? Especially next week when we move into series and parallel circuits, we have to understand what is in series, what's in parallel, how are all these things going to combine together. So really an equation is just simply a string of variables put together. We need to know how to manipulate them, how to put them into the formulas, things like that. So, for example, basic formulas that we have, voltage is equal to current times resistance. This is an equation. Even though it has two variables, it's still considered an equation. So, if our current equals 7.5 milliamps and the resistance equals 2.7 kiloohms, what is the voltage? How do we put this in there? 7.5 milliamps multiplied by 2.7 kiloohms. Okay, we can, like I said, this is as simple as an equation as we can get. So what comes up to be our answer? 20.25 volts. And then one thing we want to look at is when we're in our equation is we want to make sure all of our units are taken care of. So in this, we have amps times ohms. So in the end, really, we have 20.25 ohm amps. But we know that an ohm multiplied by an amp gives us a volt. So everything still works out. So when we're in these equations, pay attention to the different types of units, especially when we start doing multiple level conversions, like converting degrees Celsius to degrees Fahrenheit, to converting miles into kilometers, things like that. Make sure that as we're doing these steps that your units are canceling out the way they're supposed to, or they're merging to form the correct units. This will also help maintain your answers as well, so you don't do what I did and multiply volts times volts to get ohms. It does not work. I got ridiculed. Okay, so another complicated formula. Let's look at this. So we're going to take the square root of 3xy plus yz squared. And in this instance, x is equal to 3, y is equal to 5, and z is equal to 4. So this exact formula we may not necessarily ever use or be something, but we need to understand that we're going to have formulas that we build that are going to look like this. Okay? When we go through and put this into our calculator, we need to make sure we enter everything in correctly. So we have a couple ways to do this. We can go through and break this up individually. We can plug all the numbers in and then plug it into our calculator. So we just have to understand what are we doing. So we take the square root of 3 times 3 times 5 plus 5 times 4 squared. Okay, so when we look at this, let's kind of combine all this stuff together and let's simplify it as we go. So 3 times 5 is 45. Plus 80, which is 5 times 4 squared. So then we have 45 plus 80, 125. And the square root of 125? 11.18. Yes. And then depending on what, and that's a good point. When you're finding the square roots, it's going to be plus or minus. Usually we're going to be finding this in terms of like resistance or things like that. And in our case, we can't have negative resistance, so that negative side just falls off. Even if we end up with a negative answer, it still is going to be positive because it's resistance. Time, when we get into the time, we're not going to have negative time because we can't go backwards in time. So all we can look at is a snapshot from when we started up to a certain point, and that starting point is going to be our 0. If we end up with a negative time, we've probably added an extra negative sign in somewhere. So yeah, you take the square root of 25. That's what this is. This is the square root symbol. It's also to the 1/2 power. So there's 2 ways to do it. This conversion is important when we start getting into some of these complicated ones where we have things that are squared, raised to the 3rd power, cube root, that kind of stuff. It makes them a lot simpler as far as looking at them. For one, you get rid of that nasty square root. But 2, it's a little bit easier to enter into your computer or your calculator. You just hit to the, and then in parentheses, a fractional power. And for most of the times that we're going to be doing this, we want to solve it down to the actual decimal value because we don't want that square root symbol in there. It's an extra step that we're going to have to do later. Plus, when we're measuring stuff, it's not going to give us, what is it, 5 root 5? It's not going to give us 5 root 5. It's going to give us 11.18 amps or ohms or whatever it may be. So basically, this is the whole idea is we're going to come up with some formula. We're going to throw our variables in. This is usually going to equal some other variable, and we can go back and forth. We could even go through this guy and solve it. So let's say this is t is equal to this. Let's say we didn't know what 5 was, or what that y was equal to 5, but we knew the answer was 11.18. We could go through and we could solve for what that y value is. Basically, when we have our formula, we can go either direction to solve any of our unknowns. And usually we want to set these up into a point where we only have one unknown. In this case, it was our answer. Any questions about that? Like I said, it's just understanding how, when we're given a formula, we're given values, plug it in, solve for whatever we need, whichever one we don't have. All right. So we're going to talk about prime factors and lowest common multiples again. But this time, instead of just one term, we're going to have multiples. So we have 75. Let me change colors on this. So let's say I have 75 times x cubed times y squared. I want to be able to factor this guy down. So when we do this, we're going to factor it just like what we did with regular numbers. So starting with this guy, 75, we can break up into what? 3 and 25. The 25 breaks up into 5 and 5. Okay? The x, so our x cubed, can be broken up into an x and an x squared, which can then be broken up into an x and an x. We want to take everything down to its prime. Our y times y. So we end up, so with this finally factored all the way out, is 3 times 5 times 5 times x times x times x times y times y. Now this may seem a little counterintuitive because when we're trying to do this, usually this is going to be the correct form for an answer. We don't want it completely broken out like this. For one, that's a lot of stuff to have to write. It's a lot easier just to write 75x cubed y squared. But we need to be able to break these guys down, especially when we have variables like this, into separate parts, because when we start adding and subtracting and multiplying and dividing, if we can get some of these to cancel out while we're working the problem, it's going to make it a lot easier for us in the end. So one more example. We have 14ax squared. What's the factors of that value? 2 and 7. X, and A. And that's it for factoring it. But again, like I said, the part where we want these values to be factored out. This is the more correct way. This is the reduced form. But taking that into effect, let's look at specifically lowest common multiples of these guys. So we have 3ax squared and 7a squared b. We want to find the lowest common multiple between these guys. So if we were just to brute force this, we take everything multiplied by everything else. So we have 3 times 7, which is 21, a times a squared, which is a cubed, b, x squared. So if we just brute forced it, that's the value we would get. Now, that could be the lowest multiple, but we always should check to see if there is a smaller one, just because it's going to make our answers easier to simplify later. So first thing we want to look at is the factors. So between 3a and x squared, we have 3a, x, and x. The 7, we have 7, a, and b. So now looking at this thing right away, what's the one thing that I noticed that we can change in here? The a's. We don't need to have 3 a's in there. Especially if we're going to be using this later on in another formula, having to multiply another value, that's just more keystrokes, that's more time, that's more opportunity for error to enter into our calculations. So once we factor these, we look at the lowest common multiple. Well, for this guy, we need a 3, an a, an x, and an x. We have to. Easiest thing to start with is you take everything from the first term. Then we come to the second term and we look. Well, what do I need now? I need a 7. I need an additional a and a b, because I already have my second a right there. So then the lowest common multiple for this guy turns out to be 21 a squared b x squared. So like I said, you may not think that that's much of a big deal, but what if this was 21? Well, now, instead of this being 21, this becomes 63. Or we come back down to this and we still end up with 21. So, like I said, the least common multiple, it allows us to find the smallest number to eliminate adding error into our calculations. It gives us a smaller subset of things to have to multiply together. Then we would go through, use this equation when we're doing fractions specifically. Okay, any questions? Like I said, it's just a continuation of what we did last week, but it's a little bit more complex because now we're throwing in variables. Does anybody have problems with letters being in math? I guess I should start with that question. It's not an easy topic. It really isn't. And I'm not saying that to pick on you guys or anything, but that's the heart and soul of electronics. Is it's math riddled with letters. Programming gets into the same way too. So, but just be aware if something's not quite making sense, especially when we start getting into some of these complex formulas, please say something, and we'll go back and rephrase it, reword it. I want you guys to understand this material. Okay. Another reason this is important, when we start getting into the multiplication and division of polynomials, or monomials, sorry. So what's a monomial? Do you guys know? One number, one term, okay? And a term is defined as something that is together that's not separated by an addition or a subtraction sign, okay? So we have 6a squared x cubed divided by 2ax to the fourth. Now, that does look like a big, nasty, gnarly formula, okay? But one of the things we can realize is what we're trying to get you guys to do is start realizing these patterns on what you can and can't take away. So, factoring this guy out, we're going to have a 2 times a 3 times an a, an x, and a 2, and an a, and an x. So just real quick, we could break these apart and look at them. Now, when we're dividing, now this becomes really easy. I've got a 2 on top and a 2 on bottom. Cross it out. They're immediately gone. I have an a and an a. Cross it out. I've got 3 x's. And cross out 3 x's. And so then, now we're quickly reduced with a 3a all over x. So when we break things up with our prime factors, we can usually simplify these equations down. A lot of times we're going to try and do this in where we get terms with previous formulas that we've worked on. So like a Kirchhoff's formula, where we have a subset of it where we have voltages and currents. We can combine those together. We could even combine them together from a previous step to get rid of, like, if we have 2 unknowns, like 2 different currents that we're working through, we could combine this from a previous step into this one and start simplifying a whole bunch of different things down together, because as long as we treat things as equals, then we'll be able to reduce these down. Okay, what's the other way we could have looked at this without dividing it out, without breaking it down into the factors? Do what? Yeah, we can combine the like terms to start with. Also, this is just the same as what we were doing with the powers of 10. Doesn't matter the base that we use as long as it's the same. So here, we can split these guys up into 3 groups. Okay? We have 6 divided by 2 gives us 3. We have an a squared divided by an a, so that is a, because we subtract the powers. So we have a to the 2 minus 1. Then we have x, which is 3 minus 4. And here's a cool trick. So we end up with 3a x to the negative 1. When you have a power to the negative 1, you can bring it down. Yep. So you can flip things back and forth from the numerator to the denominator as well. You want to try and end up to where you don't have negative powers in the end. You want those to be positive as much as possible. If you have a negative in the denominator, it would flip it up to the top. Make sense? Okay, same thing with multiplication. Sorry, I had too many Z's and 7's and 2's in one line. My brain shut down. So same way, when we're multiplying numbers like this, if they have the same base, we can apply the same powers of 10 rules. Okay? So we have 3 times 4 times 7. So we got 12 times 7, which is 84. Then we have A, there's no other A's. B, we have a B squared and we have a B, so it would be to the 2 plus 1. We have an X, and it's by itself, so it's just X squared. And then the last term we have is a Z to the 1 plus 2. So then we end up with 84, A, B to the third, X squared, and Z cubed. So all we're doing is we're just complicating everything. But that's part of what electronics does, is we're building up and building up and building up. Even when you guys get, like I said, at the end of next week, we're still adding on to series knowledge. When we get through today, we're going to add parallel to your repertoire. Then tomorrow or next week, we're going to combine the two of them together. Then the week after that, we're going to start talking about different situations where you have circuits, multiple batteries, different current sources. Specifics that it's really hard to determine if things are in parallel or in series and what they're in parallel and series with. That's going to be one of the fun opportunities that you guys get to do. Okay. And you can also combine these guys together, doing multiplication and division in several steps. So if you have fractions, exact same rules are going to apply. What can I multiply together? What can I separate out? How can I reduce this down until I get to my final answer? And if you reduce them through as you go, cross-multiplying, that kind of stuff, it's going to make your answers easier to solve. Questions about the multiplication of monomials. Polynomials are 3 or more. We'll get into those later. Okay, so multiplication and division of fractions. Again, the same thing. We're just talking with variables and stuff into them. So we have 5a squared times b divided by a 3ax, and that's multiplied by 21xb divided by 30a squared b. So right off the bat, we could go through and we could split everything up into their factors, lay it out, cross-multiply, divide everything out individually, or we could just start applying some of our rules. So since we're having these multiplied, this is going to be 5a squared b 21xb all over 3ax 30a squared b. Now I'm not doing anything extra with them, I'm just combining everything together. When we're multiplying, it doesn't matter the order. We can shift these around a little bit. Okay? So if we combine everything together, is there anything now that we can completely eliminate? Like terms. So in this case, we have an a squared on top and a squared on bottom. We don't have to multiply the a times a squared and then divide that from in there. We can just remove it right off the bat. We have a b and a b and an x and an x. Anything else we can eliminate? Yeah, you could do the 5 by 30. So this turns into 1, this turns into 6. 1, 7. So now, all that's left, 7b over 6a. We didn't even have to go to this step to do it. We could keep it in this form. And again, we could see we've got top and bottom, top and bottom, that one and that one. And either way, we can still get to the same answer. Like I said, we could also take it and factor everything out into its prime factors if you need to do that. Okay? You don't have to always do the prime factors if you don't want to. Everybody okay with that? Okay, division of fractions. So we have a fraction divided by another fraction. One of the things to always look at as well is when we're doing these is division, not the funnest thing to do with fractions, monomials, anything. Multiplication is easier in my opinion. So, remember the trick that we have. We can invert and multiply the second term. Turn it into a multiplication problem. So this guy will convert into 3a squared times b over 4ac squared times 2bc over 6ab squared. So now we're back into this where we were at before. The biggest thing is, remember, if we divide by a fraction, we can take the divider versus the dividend. Can't remember, I think I got this backwards. We take our second term, we invert it, and we multiply it. Not in this instance, because that's incorporated in this change from division to multiplication. If we were just to move it, then yes. But by taking the inverse and multiplying, converting it from a division to multiplication, that doesn't happen because that's included in a separate step. So then in this case, now we can go through and we can do the same thing that we just did. Okay? We have an a squared over an a, so the square is going to fall off, and that one's going to fall off. What did you say? 1 over 4c is one answer. Okay? I think yep. Those two b's will cancel. One of the c's cancels out. So yeah. So in the end, we got rid of this whole term. Or those whole two terms, I guess you could say. We end up with 1 over 4c. Like I said, you're not going to have necessarily this specific type of problems, but you're going to have these same concepts when we get going with our formulas. To be able to understand how the steps are to convert them, how we need to find, how do we do division of fractions, especially when they start getting complicated. Because we're going to have currents, powers, voltages, resistance, all sorts of stuff running through these. And just understand that at the heart, this is all they're doing. If you need to leave it in terms of like this, so let's say we're running through and you have, 3 ohms times your current times voltage times whatever it may be when we get this formula, leave them in these terms, to help you solve it. And then remember to substitute them back for them. There's no rule that says you can't make your own substitutions as long as they are equal and they don't actually change your problem. So just for ease, if you wanted like B to be your resistance or your current measurement, and let's say you had B equaled like that, 472 microamps, instead of having to write that out, you could just put it in as B and then solve for your equation and then put it back at the end when you need it. It's a very legit thing to do. It'll help save some space. It's a lot less writing, but it's also adds a little more complication because then you have to remember, what do my symbols mean? Okay. The last math topic that we're going to talk about today. Anybody have any problems with the division of fractions? Adding and subtracting fractions. This is kind of where it all comes down. A lot of times we're going to have situations where we're going to have fractions such as this. 1 over 3ax plus 6 over 3a plus 5x over 7a. We're going to have these things come up where we're going to have different bits and pieces, different units that's going to be multiplied together to give us values. Because, for example, we have voltage or power, either one, take your pick. We could end up in theory with, come on. So we know, for example, in Kirchhoff's voltage law, we have our voltage source minus okay, let's say we had 3 resistors. This has to equal 0. Okay? So whatever we have input has to be dropped across those guys. We'll talk about this a little bit more when we get into some of these other theorems. But the idea behind this is all of these are going to equal out. Our source is going to equal the drops across all the resistors. Well, when it comes to the fractions, for voltage, we could have the square root of power times resistance. That's voltage. We could also have power over current. And we could have current and resistance. So right there, we're talking about 3 of the exact same things. We're talking about voltage in all 3 cases. But all 3 of them are written out in a little different form depending on how we measure them. Sometimes you're going to get homework problems that are like this. You're going to get things expressed in terms of power and resistance, and then you need to solve for current and voltage in those guys. So this is kind of where this is coming into play. So if I've got this value here, I need to go through and I need to convert everything first off into the same denominator. Otherwise, I can't add and subtract them. So again, we're going to go back down to our factors. So in this case, they're pretty easy. They're already spelled out for us. We need to make them all, what is our least common multiple with these guys? 21ax. That's what we're shooting for. And how do we get there? Yeah. Do what now? You're on the right track. You're on the right track. So basically, this is what we have to get the denominators to so we can add them together. So we're going to end up with 3 terms all over 21 over ax. So now how do we get there? This first one, what do we have to multiply it by to get the bottom to be 21ax? we need a 7. So we have to multiply this whole thing by 7 over 7. So that's going to convert this bottom to 21ax, and our top becomes 7. Okay, this next term. What do we need to multiply the denominator by to get to the 21ax? 7x. So we multiply both the top and the bottom by 7x, because 7x over 7x is 1. And if we're multiplying our equation by 1, we're not changing it in any way, shape, or form. Just how it looks. So we end up with 42x over 21ax. Now we come to the last one. What do we need to multiply this guy to get to our 21ax? 3x. So we multiply both the top and the bottom by 3x, and we get 15x squared. Then we can combine everything together and get one term, because now we have a trinomial, 3 different terms. Yep. Well, 15x squared plus 42x plus 7 all over 21ax. And we're going to leave it in this form for now. I think it's next week or the week after we will actually go through and we can do this division. And turn it in. So right now, this is an improper fraction. After we're done, we can turn it into a mixed number, or a mixed polynomial, I guess I should say.
Oh, never mind. I just realized we got to the x squared.
Yep, because we got, yeah. Yep. X times x up there, yeah, you're right. That would be the answer. Because right now, we're not going to simplify it down any farther. Sometimes we don't have to, but right now, this is, that's a combination of everything, and we can solve it from there. Because there will be times where we'll want to solve for that x value. That's where it starts to get fun. Moving everything around so the x's are by themselves. But it gives us one term to work with. Okay. Any questions about the math that we've covered so far? Like I said, sometimes it's going to take just a little bit of practice. If you do need help, please, please, please come talk to me. I'm here after class until 5 usually. I'm in my office between lunch and that kind of stuff from 11 to noon. But yeah, come see me. So, let's see. It's up to you guys. You want to continue to learn parallel, or do you guys want to leave early?
5 minutes left.
Not sure that clock is off. Yeah, we'll let you guys go early. That clock's about 5 minutes slow. So.